Welcome to Online Precalculus. This is section 1.5, more on slope. Our objectives for this section are to find slopes and equations of parallel and perpendicular lines, interpret slopes as a rate of change, and finally, find a function's average rate of change. Okay? So let's take a minute here, just look at these two lines. Okay? From what we know about slope, we can tell that both of these lines have a positive slope. They're both going up from left to right. And we can sort of analyze a little bit about what they mean from the data, from the number of US adults ages 18 and older living alone. And you can read this section a little bit down here, but the point is if you look really carefully at the graphs, if you look at the graphs of men and then at the graph of women, you can tell that the graph of men is going up slightly faster. The green graph is going up slightly faster than the red one, than the women. That means it has a greater slope. So this tells us something about what is going to happen to these things over time by analyzing the slope. And that's kind of what we're going to do in this section, is not just calculate slope, but use slope to help us analyze different things, okay? But first, before we get to the word problems, before we get to the analyzing graphs, let's talk about how to find parallel and perpendicular lines. So, two non-intersecting lines that lie in the same plane are called parallel. And if two lines do not intersect, the ratio of their vertical change to horizontal change has to be the same. They're going to have the same steepness. They must have the same slope. And that is actually the definition of parallel lines. Parallel lines have the same slope because they never intersect. So you can see that in our little description right here in the yellow box about slope and parallel lines. And if two non-vertical lines are parallel, they have the same slope. And we can say that the other way as well, that if two distinct non-vertical lines have the same slope, they are parallel. And two vertical lines, both with undefined slopes, are also parallel. So there's pretty much a standard type of question that you're going to be asked about equations of parallel lines. And it is, given a point and a different equation, a different line, find a parallel line that goes through that point. Find a line parallel to your other equation. Okay, so if you see this question here, write an equation of a line passing through 3, 1, parallel to that line right there. Y is equal to 2x plus 1. And we're going to express the equation in point slope form, which is good because that's what we're going to have to start with, and slope intercept form after that. Okay, so first, to have point slope form, we need a point. Well, the question gives us a point, -3, 1. We also need a slope. And because I want these two lines to be parallel, the slope is going to be 2. Well, that's great. Okay, so now let's use point slope form. Y minus y1 is equal to m times x minus a -3 turns into a positive. And that's my equation in point slope form. Then to change it to slope intercept, I just need to solve for y. So I'm going to distribute the 2 and add 1 to both sides. So y is going to be 2x plus 7. Notice that my answer has the same slope as my original equation. That's good. We wanted a line parallel. Parallel lines have to have the same slope. Okay, let's try our checkpoint. Okay, so again, we have a point and we need the slope. So my point is -2, 5, and my slope is 3. So I can now write the equation in both point slope and slope intercept form of a line that goes through -2, 5 and is parallel to y is equal to 3x plus 1. So my equation y minus y1 is equal to m times x minus a -2 Distributing, that was point slope. Now let's turn it to slope intercept and add 5 to both sides to give me 3x plus 11. Okay. Next, two lines that intersect at a right angle are said to be perpendicular, kind of like the two in the picture down there. Okay. Perpendicular line, the relationship is not quite as obvious as parallel. Parallel is right, nice and easy. You take two lines, if they have the same slope, they're parallel. But if you look at the two lines that are perpendicular, the red line's going down from left to right, the blue line's going up from left to right, so they clearly have different sine slopes. And if the slope is rise over run, if this was sort of a line that was rotated these 90 degrees exactly, you can see that the slope would be kind of the same, except here C is going up, D is going right, but here C is going left and D is going up. So my slope of the red one would be negative D over C, right? To get from B to A, I would have to go down and then right. And then to get from left to right, we would go up and then right there. So this would be a positive C over D. Notice that let's get all of this in case you want to read any of it, that the product of those two slopes is -1. This will always be true, okay? So here's my theorem right here. Two non-vertical lines are perpendicular, then the product of their slope is -1. And then the opposite is also true. If the product of the slope is -1, then the lines are perpendicular. And then a horizontal line having 0 slope is perpendicular to a vertical line having undefined slope. And if visualizing how two fractions multiply together to give you 1, the other relationship that we can say is that if one line is perpendicular to another line, they have negative reciprocal slopes. So that means, like, if the first slope is 5, the next slope would be -1 over 5. The opposite fraction, the reciprocal, and one is positive, one is negative. So if one slope is -3 over 4, the other one is 4 over 3. Back to my original, C over D, flip it over, D over C, change the sign. The product of those will be -1. Okay, so similar question here. Write an equation of a line perpendicular to something else. So first, we have to find the slope of a line, and then if I want a line perpendicular to that, I have to have the negative reciprocal slope. So that equation is in general form. X plus 4y minus 8 is equal to 0, set equal to 0. In order to figure out the slope, I just need to put it to point slope form, to slope intercept form. So I'm going to subtract x from both sides to give me 4y minus 8 is equal to -x. I'm going to add 8 to both sides. So 4y is equal to -x plus 8. And then I'm going to divide everything by 4 to give me what's a 1 on the top, plus 2. So that means my new slope of a line that's perpendicular is going to be the negative reciprocal. That's negative, so negative and negative is a positive. And instead of 1 over 4, I just put 4 over 1, which is just 4. So my new slope is 4. Then write an equation that goes through a different point. Okay, so, well, I can't express the equation in general form. I can't express it that way right off the beginning. I have a point, I have a point, 3, -5, and I have a slope of 4, which is perpendicular to my line. So I'm going to have to start with point slope. Y minus y1 minus a minus turns into a plus equals m times x minus x1. Distribute. My goal for general form is to set it equal to 0. So subtract 4x from both sides and add 12 to both sides. So I get -4x plus y plus 18 is equal to 0. And then I can multiply everything by a -1 if I wanted to in order to not have the equation lead with a negative. All right, so, oops, a little big. Okay, find the slope of a line that's perpendicular to a line, and then write the equation through a different point. So let's do both of these together. So first we need to find our slope. So we have x plus 3y minus 12 is equal to 0. I need to get y by itself, so I'm going to subtract x and add 12 to both sides. Dividing out the 3 gives me y by itself, -1/3 x plus 4. So my new slope is a positive 3, the opposite reciprocal of -1/3. And then I'm going to go through -2, -6, right? That's the point I want to go through. So point slope, y minus a minus 6, 3 times x minus a minus 2. So y plus 6 is equal to 3x plus 6. Subtracting 6 from both sides just cancels these two out. And so we have a -3x plus y is equal to 0 in general form. All right. So let's talk a little bit about slope as a rate of change. So slope is defined as the ratio of change in y to a corresponding change in x. It describes how fast y is changing with respect to x. When you have lines, right, for linear functions, slope can be the rate of change of the dependent variable versus the unit change of the independent variable. When we have something other than lines, that we might have to adjust that a little bit, but when we're looking at a straight line, we can kind of tell what the slope represents. Okay? And always, when we're solving in applied problems, keep track of your units that are in the numerator and the denominator. So here's our graph from the beginning. So this is the number of women and men living alone. Find the slope for women, and then for our checkpoint problem, we'll find the slope of the men. So we'll just do both. Okay. So first, let's do women, which is the red line. So the slope is the change in y, y2 minus y1 over x2 minus x1. So this is y2, this is y1. Doesn't really matter to find the slope here, but we do like to go left to right. So the change in y would be 18.3 minus 14.0 over the change in x, 2008 minus 1990. So subtracting those two gives me 4.3 over 18, which is about 0.24. But what does that mean? Okay, well, the change in y is millions of women. That is the y. So this is 0.24 million. Let's say women to differentiate. Per, I ran out of room here, per something. Well, the bottom of this is years. So we can say that every year there is 0.24 million more women living alone. And that's sort of what this data is telling me. Okay. And then, like I said, the checkpoint is to find the slope for the segment for men. So we're going to do the same thing. Okay. So for men, right, y2 minus y1 over x2 minus x1. This was 14.7 minus 9.0 over still 2008 minus 1990. Double check those numbers, right? 14.7. Did I get that right? Yeah, 14.7, 9.0. Okay, so let's calculate this slope. So we get 14.7 minus 9 is 5.7 over, and that's still 18 years. So divide by 18, and we get 0.32, 316, repeating. And again, this means that there's 0.32 million men per year. Okay, that's how many more, and that's more men per year because the slope is positive. Slope is negative, then it would be less, right? Then less people would be living alone every year, but this time there are more. Okay, so now let's talk about the average rate of change of a function. So if the graph of the function is not aligned, the average rate of change between any 2 points is the slope of the line containing those 2 points. And when you connect a graph through 2 points that intersects the graph at both of them, that is called a secant line. So if you look at this picture of this boy growing up as he gets older and older, you can see that some years he grows fast, some years he grows a little bit slower. Some years it looks like he flattens off a little bit. Not quite, but a little bit. And we can see the 2 points here. 13 years, 57 inches. 18 years, 76 inches. So this guy's average rate of change, if I wanted to find it over those 5 years, would be the change in y over the change in x. So I'd just do y2 minus y1 over x2 minus x1, and we would get 19 over 5, which is 3 4/5. So this person grew about 3.8 inches per year over that time frame. So if you pick different points, that the slope of that line is going to change. Okay. And here's my formula for average rate of change of a function. So it's just same thing, y2 minus y1 over x2 minus x1, but now we can use function notation, right? We can say that the function evaluated at x2 minus the function evaluated at x1. So f of x2 minus f of x1 over x2 minus x1. This is important, however, since the slope is not always going to be the same, you should always put x1 first and then x2 further to the right on the number line. Okay? So definitely keep that in mind. Okay? So find the average rate of change of f of x squared from 0 to 1. Okay, so we have to find f of x1 and f of x2. So this is going to be f of 0 and f of 1. And my function is x squared, so I just plug it in. So that is 0 and that is 1. So now that I have those, I go, my formula is f of x1, f of x2, minus f of x1 over x2 minus x1, which is going to be 1 minus 0 over 1 minus 0, which is 1. Okay, what about from 1 to 2? Now this is going to be a little bit different. So we want to find f of 1 and f of 2. Well, 1 squared is 1, but 2 squared is 4. So now my formula, f of x2 minus f of x1, is going to be 4 minus 1 over 2 minus 1. So that's going to be 3 over 1, which is 3. So definitely a difference of slope. And think of what a parabola looks like, right? So if we think about a parabola, right, f of x, x squared. So if we have our graph right here, to go from here to here, slope of 1. But if I go from here to here, right, the slope is much steeper. Then what about from a negative? So now we have f of negative 2 and f of 0. F of negative 2, 2 squared is still 4. F of 0 is 0. So now here's where it's important. Remember which one is x1, which one is x2. So it's 0 minus 4 over 0 minus negative 2. So that turns into a negative 4 over a positive 2, which is the slope of negative 2. Okay? And that makes sense if you think about a parabola going from a negative 2 to a 0. Right now my slope is going down. So it is very possible to have all these different slopes in a function. Let's try cubic. Okay, so f of 0 cubed would be 0. F of 1 cubed would be 1. So similar to the first one, f of x2 is 1 minus 0 over x2 minus x1, which is 1. For part B, we would have f of 1 would be 1, but f of 2 would be 8, right? Because we're plugging into x to the third power. So now f of x2 minus f of x1 over x2 minus x1 gives me, that would be 7 over 1, which is 7, so a much higher slope there. This one might not turn out the same as the parabola because f of negative 2, f of negative 2 is negative 8, and f of 0 is 0. So f of x2 minus f of x1 over x2 minus x1 now gives me a positive 8 over 2, which is 4. And if you think about what a cubic looks like, yeah, you can see that if I'm going from a smaller number to a bigger number, right, if this is the axis, right, negative 2 to 0 is going to give me a positive slope. 0 to 1 is going to give me a positive slope, and 0 to 2 is going to give me a much bigger slope. Terrible picture there, but we'll deal with those in the next section. Suppose for a second that you're interested in finding the rate of change, the average rate of change of a function from x to x plus h. So when you calculate this, look at what happens. You get f of x plus h minus f of x over x plus h minus x. The x's cancel, and you're now just over h. That is how you calculate the difference quotient that we used in section 3. Okay, so then that means that the difference quotient gives you the average rate of change of a function from x to x plus h. Okay, and in a difference quotient, h is a number very, very close to 0. So this way, the average rate of change can be found for a very short interval. And that is the beginnings of calculus, finding limits and derivatives. Okay, so let's not worry about that too much, and let's find the average rate of change of this function right down there. So when a person receives a drug injected into a muscle, the concentration of drugs in the body measure milligrams per 100 milliliters. This is a function of the time elapsed after the injection, measured in hours. So let's find the average rate of change between 3 and 7 hours. And I have my 2 points right there. I have x, I have f of x. All I need to do is calculate this. So we have, remember my formula, f of x2 minus f of x1 over x2 minus x1. F of x, this is x1, the 3, this is x2, because it comes second. And you can hopefully tell that the slope of this is going to be negative. Okay, so f of x2 would be 0.02 minus 0.05 over 7 minus 3. So when we calculate this, we get negative 0.03 over 7 minus 3 is 4, which is 0.0075, negative 0.0075. Okay? So that means the average rate of change is negative 0.0075 milligrams per 100 milliliters, this thing, per this thing. So yeah, there's a lot to say on the y-axis, but it's always y over x. Let's try a checkpoint between 1 hour and 3 hours. So at 1 hour, we can see my point right there is going to be 1 comma 0.03. Oh, 0.3. Yeah, ugly. Whatever. Okay, so let's try it. All right, so my formula again is f of x2 minus f of x1 over x2 minus x1. Okay, but this time f of x2 is the 3 hours, so that's 0.05 minus 0.03, which we got from x1, and then it's 3 minus 1. So this is going to be 0.02 over 2. And so we get 0.01, a little thing. Okay, and what's the units? Milligrams. Let me write it out. Milligrams per 100 millimeters per hour. Okay, the y unit, whatever it is, divided by the x unit. Okay. So, can you clarify how to determine the units that you use when describing slope as a rate of change? We always do exactly what we did. The unit for y per the unit per x. Just pile them up, one per the other. Okay. Oh, this can translate directly to average velocity. So average velocity is its change in position divided by the change in time between the starting and ending positions. So if the function happens to express an object's position in terms of time, the average rate of change describes the average velocity. So as long as our function describes the position in terms of time, the formula for average velocity is exactly the same thing as the formula for rate of change, right? But instead of f of x2 minus f of x1 over x2 minus x1, we just have a function, a position function in terms of time. Okay? And we can calculate this exactly the same way by finding the slope of the line between the two things. Okay, so if we have my position function right here, s of t, all we have to do to find the average velocity from 2 seconds to 3 seconds is plug in 2 seconds. So, whoops. So s of t1 would be s of 2, which would equal 2 squared is 4 times 5 is 20 seconds squared. And s of t2 would be s of 3, which would be 45. Okay, so we would have 45 minus 20 over 3 minus 2, which would be 25, but now we need a units. Okay, the distance in feet, so s of t is feet, so that's feet, over time, which is per second. So feet per second. And sometimes when we write feet per second, right, we can write feet per second like that. Either way, it's good, right? Because we're doing 25 feet per 1 second. Okay, and we're getting that just by getting the units. The units of y was 45 feet, 20 feet, and 3 seconds, 2 seconds. Feet per second. Units stack up. The units of y divided by the units of x. Okay. Next, we can see that these slopes are going to be slightly different. So, right, let's go delta s over delta t, same thing. We're going to go s of 2.5 minus s of 2 over 2.5 minus 2. Right? Instead of writing the whole thing out, we'll just do that. So 2.5, when we plug that in, we get 31.25 minus 20, right? The 5 times 4 over 2.5 minus 2, which gives me about 22.5 feet per second. And then the last one, so you can tell that the second one, the slope was smaller. And the third one, the slope is going to be even smaller than that. So when we do the third one, when we get, when we get delta S over delta T, which would be S of 2.01 minus S of 2 over 2.01 minus 2. And that gives us, calculate 2.01 squared times 5, gives me 20.2005 minus 20 over 0.01, which is about 20.05. And again, this is going to be feet per second. Okay. Let's just do one more of those real quick with our checkpoint problem. Let's not do all three. We'll just do the first one here. So we got delta S over delta T. So that's going to be S of 2 minus S of 1 over 2 minus 1. S of 2, 2 squared is 4, times 4 is 16. S of 1 is 4 over 1 to give me 12 feet per second. And then same thing for the next. And the slopes of those, because it's a parabola, right? The slopes as you get closer and closer and closer to the point where you're starting, the slope is going to get lower and lower. So that 12 feet per second is going to go down. All right, and that was section 1.5, more on slope.